can now move on to look at the transmitter tests. And what we're trying to do here is verify that a product's transmitter is within the specification. So in order to do this, we have to use that direct test mode to get the device under test to transmit signals in the channels with the payloads that we want in order to do the test. And then we're going to verify the transmitter for power, in-band emissions, modulation of the carrier, and the carrier frequency offset and drift. So I've split the slides really to cover what the DUT is doing, the tester parameters, the procedure, and the limits. So if we look at power first, what we're doing here is we're measuring the transmit output power across a 3 megahertz band. So you can see the resolution bandwidth is 3 megahertz. So that's really the measurement filter. And the frequency span is 0 megahertz. So if you're aware of a spectrum analyzer, what you tend to do with a spectrum analyzer normally is you'll have a start frequency and a stop frequency, and you'll sweep that measurement. So the analyzer will sweep the measurement across the frequency band. Here, because we have 0 span, what you're doing is just measuring the power in a 3 megahertz band, window over time. So it's really just a power measurement. And we measure both the peak power and the average power. So for the limits, up to Bluetooth 4.2, the limits were minus 20 dBm to plus 10 dBm. That now goes up to plus 20 dBm. And the peak power has got to be within 3 dBs of the average power. The next test is for in-band emission. So what we're looking at here is the power in the LE band, but in other channels. So we're trying to simulate other Bluetooth LE devices within the range of the receiver. This time we're looking at a 1 megahertz frequency span with a narrower bandwidth of 100 kilohertz. And we measure the power across each band or each 1 meg step from plus and minus 450 kilohertz in 100 kilohertz steps. And then we increase the center frequency by 1 meg and repeat that measurement. And we do that measurement across the whole band, but we skip the transmit channel that we're using because this is emissions in the other channels. And we skip that band plus or minus 1 megahertz. So for those 3 frequencies, we don't do a measurement. The power has to be below minus 20 dBm, which is the lowest power that's allowed for a transmitter, if you remember from before, within 2 megahertz of the transmit channel, and then minus 30 dBm for the other frequencies. And there's a relaxation here of you can have 3 of those measurements with a minus 30 dBm limit, as long as the limit is still within minus 20 dBm. Then the next test is a modulation of the carrier frequency. So this is how a product encodes the binary data. For this test, we use 2 different payloads, a 4140 payload, which is actually the transmit sequence is reversed for these, and then the 1010 alternating payload. So we measure the modulation first of the 4140 payload, and we calculate the average power over that entire payload, and that becomes F1 CCF. We then look at the stable bits, which are bit 2, 3, 6, and 7 out of those 8 bits, and we measure the deviation from that center frequency that we've measured, and those are the delta F1 maxes for each of those bits, and then we average those delta F1 maxes to get a delta F1 average. And then we change the payload to alternating 1010 pattern, so this gives you the worst case frequency swings on the modulation, and we repeat those measurement types to give F2 versions, so F2 CCF, F2 max, delta F2 max, delta F2 average. I do have some slides coming up which sort of explain this in graphical form, which makes it a little bit easier. So the limits we're looking for is for delta F1 average to be between 225 and 275 kilohertz. So the nominal is 250 kilohertz for this 1 meg that we're looking at. So you're allowed 25 kilohertz either side of that. And almost all of the delta F2 maxes, so your deviations from the nominals, got to be at least 185 kilohertz. And then there's a ratio of your delta F1 max to your delta F2 max, which has to be greater than or equal to 0.8. So there's quite a lot of information to take in there, but the next 2 slides hopefully explain this in a little bit more detail. So for the first payload, which is the 4 bits at a time, you can see here we've got the average frequency over the payload is this red dotted line that gives us our F1 CCF. And then for the bits, hopefully you can see why we're picking bit 2, 3, 6, and 7 here, We're avoiding these where there's falling and rising edges, which could affect the results. So we're measuring delta F1 max for each of these bits, and then we then average that to give us our delta F1 average. So this plot is showing the 1010 payload. So you can see here, this is a worst case. We're swinging from a positive frequency offset to a negative frequency offset as we're encoding. And again, we measure the center frequency, which is given by this dashed line across the middle. So that's calculated over all the bits. And again, we measure the delta frequency offset for each bit, and then average those to give us our delta F2 average. So for this example, it would be around these black dotted lines for the delta F2 average. So that's the modulation. Then moving on to the frequency drift. So the frequency offset and drift of the carrier frequency. So what we're looking at is how far the carrier is offset from a perfect carrier, and then how that carrier drifts over time as well. So we're transmitting an alternating packet of ones and zeros, and we demodulate the signal and then integrate that over 10-bit sequences. So we take the first 10 bits, and that gives us our initial frequency, F0, and then for each 10-bit interval after that, we then get a series of integrals of the offset. So an integral in this case is just area under the curve, and that gives us a series F1, F2, F3, etc. of 10-bit intervals. And then we're verifying the average key frequency over each 10-bit sequence. So the limit here for Fn, so that's F1, 2, 3. This has got to be within plus or minus 150 kilohertz of nominal. Your first offset's got to be within 50 kilohertz of the nominal frequency. And then we're checking the deviation for between the first and second 10 bits, which has got to be within 23 kilohertz. And then every fifth bit has got to be within 20 kilohertz. So that gives us our drift over time. And again, this should be clearer in the slides following. So you can see here, this is the frequency offset. So within the red rectangle, that's where you can see this red dotted line. That would be a perfect signal, which would give us this nominal center frequency of FTX here. But in reality, you can see the black plot, which is the measurement that we've made, is shifted in frequency. So your actual center frequency is a little bit higher than our nominal center frequency. And what we do is we then integrate, so these green areas, we integrate for this 10-bit sequence. And obviously, if everything was perfectly symmetrical, these would give a center, as I've got here on the black line. And then we integrate these values. And the idea is to have the offset as small as possible from the nominal. But that gives us the offset, but we also have a drift over time. So this is a simplified look at the packet. We have a preamble and a payload. And what we do is we've measured the offset for the preamble. That gives us our F0. And then every 10 bits, we're measuring that offset. And that gives us this F1 to F3, etc. So that gives us those offsets. But what we need to do is make sure that offset is going to vary over time, but we want to make sure that's within limits. So we measure our F1 minus F0 offset, find the difference between that. That's that limit of the 23 kilohertz, if you remember. And then we then measure every 6 10 bits. So we'd measure the difference between F6 in blue here and F1. That would give our first frequency drift rate between F7 and F2, F8, F3, F9, F4, and so on. So that's showing us how we're drifting over time as well. So that gives us the frequency offset in the previous slide and the frequency drift. That's really the conclusion of the transmitter test.